All right, let's take a look at what we're calling improper integrals. This was an M. M-I-M, proper integrals.
Okay.
All right, so basically we got some definite integrals here with some weird bounds, right? That's what we got going on. So notice that if we were to try to integrate this and just apply our fundamental theorem of calculus, then at the end of this thing, we would get at some point, we've got a negative infinity that we have to plug into our function. We can't just direct substitute infinity. That doesn't make any sense. Notice like this right here, this is probably a good one to get a visual on. Like this is the function 1 over x, which we know that parent function. And we want to know what is the area under the curve from 0 to 1, right? So that does, like, it's kind of weird. That's super weird. So when it comes to improper integrals, just by looking at them, it's kind of hard to tell if that is going to be a limitless area, if that is going to be an area that what we consider diverges, or if that will be a finite sum. Will it converge to an actual amount? So when we have one of these situations, you can see why 0 is a problem, and hopefully we can see why infinity is a problem. The first thing we're going to do is we are going to rewrite this, and this is the first step. Without thinking, if I saw infinity as one of the bounds in my definite integral, my very first step is to rewrite this as a limit. Because I may not be able to directly substitute infinity. I might not be able to directly put a 0 into this function, but I'll be able to look at the limit as a value approaches that number. So that's always our first step when it comes to dealing with improper integrals. If this is on the free response portion of the AP exam, that'd be the first step they're looking for. That's like the 1 point right there. It's probably just rewriting it. Because once we get good at these, you probably could do it without rewriting it as the limit, but that's proper notation right there. That's how we're going to think through it. So, all right, from here, we process it like an integral, like we typically would. I'm going to use U substitution and let my stuff, my e to the stuff, be my u. And we get du over negative 2x equals dx. Still got my limit. And you could really call this anything. I typically call the lower bound the a and the upper bound the b. Basically, you just don't want to call it x because then x is something different. So we've got x e to the u du over negative 2x. The x's can cancel out. We can factor out the negative 1/2, and we can finally integrate. That's going to be a negative 1/2 e to the u kind of quick. But when we factor out that negative 1/2, e to the u integrates to be e to the u when we're integrating with respect to u. And yeah. So I'm going to now switch this back over to being in terms of x, because these are x values right here. That 0 is an x value, that a is an x value. So I've got negative 1/2 e to the negative x squared, and I'm going from a to 0. And so finally, when we do our fundamental theorem of calculus, plugging in the upper bound, that would be e to the 0 power. E to the 0 power is 1. So when I plug in a 0, I get a negative 1/2. When I plug in an a, I'll be subtracting a negative 1 over 2. And this is e to the, notice what's going on there. I'm plugging in that a, it's negative, a negative a squared. So I'm going to put it on the bottom and make this e to the positive a squared. I did some simplification there just because it's going to be nicer to not have a negative exponent. Hopefully you're able to follow that. You're able to follow that. So now, when we take our limit to infinity, negative infinity squared, still infinity, e to the infinity, on the bottom, this whole term becomes 0. It's not undefined. It's infinity on the bottom is 0. So we have negative 1/2 plus 0. And so this converged, even though we were trying to find all of the area going to negative infinity, it did converge to a finite amount. And that right there is improper integrals in a nutshell.
Fun.
Yeah, super fun. Let's look at that next one because that one's not infinity, that one's a 0. We already kind of looked at the picture of that one. So it might be, maybe we already have some assumption that it's going to converge or diverge, but let's see what happens here. So we know our first step, we're going to rewrite the limit, and I'm again going to just call it a, as a approaches 0 from a to 1. Again, it's 0 that's the problem. 1 is fine. There's no problem with putting a 1 down there. There's not a vertical asymptote at 1. There's a problem at 0. This one doesn't take U substitution or anything. We can integrate that very quick. We've got the limit as a approaches 0 of the natural log of the absolute value of x from a to 1. We can apply our fundamental theorem of calculus. So we have the limit as a approaches 0 of natural log of 1. We know what that is already, minus the natural log of a. Natural log of 1 is 0. Scratch it out. And now we really need to think about this. The limit is a approaches 0, natural log of a. And as I'm processing this, I'm realizing an even better way we could have been writing this, so I'm going to improve upon our notation. When we looked at this at the very beginning, our problem function was 1 over x, and we were looking for that area right there between 0 and 1. So technically what we even care about is a approaching 0 from the right. We don't care about approaching 0 from the left. We really care about approaching 0 from the right, and we care about everything kind of in between there. So I'm going to go back and write that in because I think that's an improved notation. I think that better describes what we actually care about. And that does make this make more sense as well. Because I'm thinking about natural log. Natural log, another parent function we know well. Natural log looks something like this. Natural log doesn't even exist approaching 0 from the left. It just doesn't happen. It doesn't exist at those negative x values. So if we were looking for the overall limit as a approached 0, well, that wouldn't be super possible. But as we approach 0 from the right, as we look at this limit of natural log, as we approach 0 from the right, we're getting out a negative infinity. As we approach x equals 0 from the right, we're getting negative infinity. So as we take this limit, we have a negative infinity, which is a positive infinity. This area, we are saying that area right there is limitless. It is boundless. It goes to infinity. It just keeps adding. And so we say that this improper integral diverges. And that would be our answer.